Bem-vindos to one more episode of the Type Theory for All podcast. This is your host Pedro Abreu, and today we have over Cody Roux, and he will teach us some very interesting concepts that people care about in mathematics and in logics as a way to try to understand what's going on in the universe around us. In particular, we will try to explain some concepts such as impredicativity, excluded middle, group theory, model theory, Kripke models, realizability, the Markov principle, cut elimination, and other stuff. You have to listen it yourself. This episode is really cool. I hope you guys enjoy it. Without further ado, let's get into it. Right, welcome everyone to one more episode of the Type Theory for All podcast. Before I introduce our guest today, I have a few notices. If you guys like the episode, don't forget to share it with a friend and to send us some comments and to share it on Twitter or Reddit, whatever. Make sure to help us out. And well, today we're going to have a guest that was here already, another episode. And it was so good that we decided to come again and talk about other very interesting things on logic, on type theory. Welcome back to the show, Cody Roux.
Thank you so much. I had a great time last time, I have to say. It's super exciting to be back on this show. This is one of my favorite things to do. Completely sincerely. It's just like a real pleasure to be here.
It was very fun. It was very fun to have you around. One thing that I think it's a good idea to tell the listener one more time. I already said this a couple of times in the show, but I think it's a good disclaimer all the time. We don't take the things that we say here as absolute truth. I'm not saying that we're trying to say things that are not truth, but we're doing our best here and we're getting things on the top of our heads, right? And I really trust everything that Cody has to say, but every now and then something might go the other way, right? Not get quite right, or some definition that is not quite the best one. So make sure that the listener to take everything with a little bit of a grain of salt and enjoy the show.
Thanks, Pedro. I definitely remember when I was a student, I'd see teachers, make small mistakes on the board, and I was like, wow, they're teachers of mathematics. People make mistakes all the time. And then when I taught myself, you go up to the board and it is surprising how hard it is to do math while you're super close to this giant blackboard. It's just very unsettling.
It's just so in the spot, right? It's
your brain just kind of slows down. It's kind of how I feel sometimes.
It's very true. Well, if you still feel like that, then that definitely makes me feel much better, because sometimes I'm just talking with people here and I feel so dumb and like, oh my god, I'm so lost now, and then I have to put a lot of effort to focus and try to understand what's going on.
Yeah, I like I said, I love these subjects we talk about, and so I just want to just like, let's have fun, let's try and kind of get a feel for what's going on, and
right.
I actually am not sure what we're going to talk about today.
Let's see where this goes, huh?
Yeah. Do you want to kind of give me a flavor of things you want to hear about, or I can also just jump into some thoughts I was having that we're discussing by email.
Right. We were definitely discussing a couple of ideas that we would like to go through. Among them, as we talked, impredicativity, excluded middle, a bunch of cool stuff inside of excluded middle. There is something that keeps popping up again and again, which is some notion of model theory as well. What exactly do we mean by models, things like that. And consistency proofs and additions to intuitionistic logic, negation of excluded middle, Markov principle. We talked a bunch of this stuff over email. Let's see where this is headed. How about
Sure.
we started by giving a flavor about impredicativity?
Yeah, yeah. This is a very fun subject, and for some reason, like I don't consider myself an expert on this topic, but whenever I Google it, my name comes up because I'm the only person that was like at the time willing to give an answer on like some Stack Overflow question. So I mean, this is a fun one for me because basically what was happening. So this is again, I'm going to talk about history, which I think I did last time. Um, so last time we talked about this like late 19th century, early 20th century kind of revolution where basically a bunch of philosophers and mathematicians got together and they were like, oh, we actually know how to write down rules, and those rules actually capture our intuition about mathematical reasoning and logical reasoning. And as I said last time, it's kind of a miracle, right? This doesn't really happen a lot in philosophy where you can just write down specific precise rules for anything really, ethics, justice, mind, all those things are this very ephemeral, but mathematics seem to be special, and people wrote down rules, they sat down, they created these syntactic systems that were relatively simple or even very simple, and it was beautiful, right? You could really capture everything that mathematicians were doing. And great, except that they noticed all of a sudden that these systems they were coming up with were inconsistent. So this is kind of the people call this the crisis of foundations, right? It was just sort of these beautiful rules that seemed to work all of a sudden led to inconsistencies, and so now it's a little scary, right? Is all of human reasoning this kind of doomed enterprise? And impredicativity is in a way these several attempts that people made to build foundational systems, really this happened several times in a very similar manner. They ended up being inconsistent, and you try to look at these systems and understand why they were inconsistent, and somehow a common theme is impredicativity, this ability to be to refer to yourself or to refer to a collections of things that includes yourself. So I can flesh this out a little bit. Basically, the first the first system that was really considered this complete foundation of mathematics was Frege. I think it's the Grundsätze system. And my understanding of that system is shaky, but basically it had this ability to perform comprehension, right? Just talk about the set of all sets that have a certain property. And in particular, Russell noticed, I can just easily define the set of all sets that don't contain themselves, right? And a moment's thought, will show you that considering the set of all sets that don't contain themselves, you can ask the question, well, does this set contain itself? And in both cases, right, either it does contain itself or it doesn't. That gives you a contradiction. And this really is like just a complete contradiction of the system. If you allow forming these sets, you can't have a consistent system. And what's kind of cute is, a few years later, Haskell Curry invented essentially a similar system called the lambda calculus. And the same kind of thing occurred in the lambda calculus, right? It was this very beautiful foundational system, but you could sort of define, the proposition that was equal to its own negation, and the same thing happens. You get a contradiction, and it wasn't obvious that you could do that in these systems. And once that had happened, it wasn't obvious what to do to fix them. And then even worse, once you've come up with a system that doesn't seem to have these contradictions, you want to ask, well, okay, well, did I really fix it? Is there still an inconsistency lurking there? And we talked about this at length last time, but basically Godot said, okay, you'll never know. Maybe there's an inconsistency, and there's just no way to know that there isn't. But at the very least, the specific type of inconsistency that was uncovered in this Frege system, you can identify, and then you can sort of try and ask philosophically, not mathematically, but philosophically, does this system have that kind of potential, for inconsistency, or this potential for self-reference that seems so dangerous? And basically, they named this potential Impredicativity, as I've already mentioned. And what's fascinating is today we have systems that are impredicative, but don't have the inconsistency, right? They just fall short. And then we have systems that are predicative, but they also have their shortcomings. And I can talk more about this in a bit.
What exactly does it mean? What should we have in mind if I say, okay, this system is predicative or this system is impredicative?
Yeah, so that's the real question. But okay, so just historically to explain the name, the name is a little bit unfortunate. Basically, impredicative means has some form of self-reference, and predicative means doesn't. But where the name comes from,
and it's also
not,
weird because it feels like it's reversed, right? Because im is some sort of negation in Latin, right? And then like the negation is actually the one that has self-reference,
yes.
right?
So okay, so I am going to explain that. I'm not sure who came up with the name. I want to say it's Russell, but that's just a guess. Basically, what a predicative system has is every construction that you can make in that system is predicated. And what does that mean? Predicated means that you can't construct a thing unless you've constructed its components, right? So let me give an example. If you take the union of two sets, right, x and y, that's a predicated construction, because if you've built X, right, predicated on the fact that you've built the set X and you've built the set Y, then it's pretty reasonable to say that you can build the union of X and Y, right? You just take all the elements of X and all the elements of Y, and that goes into this new set, right? So what's an impredicative set? It's a set that's not predicated, right? And so the set of all sets that don't contain themselves, that really refers to all possible sets, right? You look at all possible sets, and if they don't contain themselves, you put it in the set. But that set of all sets, right, that involves everything, including the thing you're trying to build, right? So the set of all sets that don't contain themselves is an impredicative construction, because it sort of says, okay, well, I'm building something, but I'm building it out of things that might include the thing that I'm building itself, right? And so, again, this definition is a little bit subtle, right? It's not a very clean definition like we're used to in modern math, right? Definitions have been fleshed out over 100 years. This is still kind of a, you know it when you see it definition. But it's pretty clear that, the set of all sets that don't contain themselves really refers to a collection that might include that set itself. And in fact, it's going to, right? That's the whole problem. And Frege used these all over the place, right? He defined the number 1 as the set of all sets that has, exactly one element. And same for 2, right? The set of all sets that has exactly 2 elements. So he really used that very powerful principle all over the place in his development. So disallowing these kinds of definitions was actually, it was a problem, right? Frege didn't know how to fix this system. And, what Russell did was, okay, well, I'm going to disallow, building any sets that refer to elements that might be that set itself. So he introduced this stratification. I guess Russell and Whitehead introduced this stratification where if you talk about the set of all sets such that something, you have that something has to be stratified, right? You're going to only talk about things that are at a lower level in that predicate, right? And so that has this property where you're only building new objects, out of things that have already been built at a lower level. And this seems much more reasonable, right? There's no mathematical proof of consistency, right? Because of the Gödel theorem. But at least intuitively, it seems pretty clear that if you're building things on top of things that have already been built, you're doing pretty good. There's no reason to expect these crazy, contradictory sets to pop up.
I see. So basically, it's a best effort in a sense that we didn't ever found a contradiction, like a killing contradiction, like the Barber's paradox here, right?
Yeah. What is scary is that so Russell and Whitehead set out to build this system, this stratified predicative system. But two sad things, I think, for them was at the same time, Ernst Zermelo came with his set theoretic axioms, right? Zermelo set theory. And that system is impredicative in the sense that if you take, the subsets of a set, right? There's this power set axiom and this unrestricted comprehension axiom that basically say that I can build, the set of all subsets of a set, right? And I can define a subset, using quantifiers that might include the subset that I'm building, right? And the other problem was in Russell and Whitehead's theory, they had to introduce this axiom that basically collapsed all the levels, right? And so they ended up basically just negating their special stratification just to be able to do what they wanted to do, which was, define normal mathematical things, right? Define the natural numbers, define the real numbers, do all this stuff. They had to basically destroy their whole stratification.
So they did everything they did for kind of nothing. They have just throw it away.
Yes. I mean,
Jesus.
they, with this additional axiom that just all collapsed all these levels, they ended up doing very well, right? They managed to define a mathematical system that allowed you to define the natural numbers and allowed you to define the real numbers and do all these things. And so in some sense, they succeeded at the foundational goal of building a logical foundation for mathematics, right? At the end, they had this incredibly dense, incredibly thick book, but you could actually say, okay, well, I see how this is going to go. I see how I can define everything mathematicians use. But in a sense, their system was needlessly complicated by this desire to be predicative, plus, this complete walk back where they collapse this whole predicative system. They're like, well, we don't love this axiom, but we're going to leave it in there because we really need it.
Is there a specific use case for that on top of your head? Like, why is it actually necessary?
Well, it's actually hard to define the reals without impredicativity.
Okay.
So this is the common example given, but I have to admit, I don't know exactly what part of the construction involves impredicativity. I do have some other examples that are a little bit more computer sciencey. And I do have, I have an example of a construction which you can either do impredicatively or predicatively, right? And it's kind of going to be clear what the difference is in some sets. So if you know what a group is, right? It's this abstract structure where you can multiply things together and you can take inverses and there's a zero and there's a unit, one and whatever. It's very useful in mathematics. People use groups all the time. And if you have a group, and you have elements, any set of elements in that group, you can take what's called the subset generated by that set, right? So you take those elements and you want a subgroup, all right? So you want a subset of that group that is also a group, and you want it to be, in some sense, minimal, right? You want it to be the smallest group that contains those elements. Okay, so how do you do it? Well, the impredicative way is just super simple. It's very simple. You just take all the subgroups that contain those elements, and you just take the intersection of all those subgroups. So this is impredicative because you're quantifying over all the subsets of the group, right? And you're taking the intersection, and that thing you construct at the end is also a subgroup, right? So it's in that set of things you quantified over. So you take all the groups that contain those elements, you take the intersection, and that is going to be the minimal group generated by the elements. And that's a very simple proof, right? It's like not even 2 lines in a math textbook. What's the predicative way of building that? Well, you take the elements of the set and you put them, in your potential subgroup. All right, that's level 0. Level 1 is you take all the inverses and all the products of all those elements and you add them to that set. That's level 1. And then level 2 is you take all those new elements and you take all the products and all the inverses of those things. And level 3 is you do the same thing and you keep going. And basically you keep going until you're not adding any new elements to this set. And then, all right, this construction is already more involved, but you can prove that this construction eventually is going to reach a stable point, a fixed point, where you're not adding any more elements to the group. And you can also prove that that thing you've built is actually a subgroup. And you can also prove that that thing you've built is the smallest possible subgroup, that there is no smaller group that contains those original elements. And okay, so you've done a lot more work, but in some sense, it's much more honest because you've really built that subgroup, right, out of things you already knew existed at a lower level. And so that really is the difference between an impredicative construction and a predicative construction. And the whole punchline of this impredicative story is that this fixed point construction, right, is very, very common in logic, right? We have all these predicative systems that have these different fixed point constructions, and they're all blown out of the water by a very powerful impredicative fixed point construction that essentially goes just like I said. You take the set of all things that are, almost the fixed point, and you just take the intersection, and it's a big intersection, right, over all the possible things, and that happens to be a fixed point, right? And this construction is so powerful that it usually it defeats, every predicative attempt of building a fixed point. So, there are actual theorems where there's like the Naster-Tarski fixed point theorem, right? That's a predicative theorem, right? You're really building up out of smaller levels. But there are much more powerful fixed point theorems where, you build things up out of smaller levels, but you might not have reached the fixed point after, infinitely many steps, right? And so you need to do another infinitely many steps, and then you need to do another infinitely many steps. And so basically in the Naster-Tarski fixed point theorem, there's this continuity requirement that says, okay, well, I don't need to do more than omega many steps. And if you remove that continuity requirement, there's still a theorem that holds, but proving that theorem becomes much harder, and you need this kind of more powerful impredicative approach. And that is really the crux, right, of predicative versus impredicative, right? In predicative, you have all this power to build these gigantic fixed points, right? Another example I was going to give was so ordinals are a type of ordered set, right? And they're basically a linear order that's well-founded. So you can't go down, infinitely many times.
So ordinals is also related to infinities,
Yeah.
the size
Well,
of
yes.
something like that.
Yeah. Basically, everybody knows what finite ordinals are, right? They're just, one, two, three, ordered using the usual order. And then omega is just the whole natural numbers ordered using the normal natural number order. And that's well founded, right? You can't count, if you pick a number, you can't count down infinitely many times from that number. But then you can go on. You can say omega plus 1 is you have that infinite line of little dots, and then you add a point at the end of that, right? And you still can't go down an infinite number of times, because if you start from that point beyond that and you go down, you're going to have to pick some natural number to jump to, right? You're going to have to jump over an infinite number and just hit one of the natural numbers. And you can keep going like that with omega plus 2, omega plus 3, and then you can stack two omegas on top of each other, et cetera, et cetera. And all this is very nice. It's very useful in logic. It's very predicative. And yeah, and you can really use those well-founded orders to like characterize like consistency, of different logical theories. It's this very beautiful correspondence between ordinals and, logical theories. Here's something that's crazy. There in classical Zermelo set theory, it's very easy to prove that there is an ordinal, so an order that's, that's well-founded and that's uncountable, that has cardinality larger than the natural numbers. And this is actually mind-bending if you try to imagine it. It's basically this set that's linearly ordered, like the reals, but where there's no infinite decreasing sequence. Now, I would challenge you to try to imagine that. It's very mind-bending. It's a very strange thing to imagine, an uncountable ordinal, a thing that has more than, a denumerable number of things, but where each time, you try to build an infinite sequence of decreasing elements, you can only do that a finite number of times, right? So this is an incredibly mind-bending thing. And it's a very powerful thing to have. Basically, a ton of constructions in logic just become trivial if you have an uncountable ordinal. In Zermelo set theory, that thing is very easy to build. You just look at the set of all subsets of the natural numbers, which happen to be countable ordinals. All right? You just look at all of those countable ordinals, and you can take that into a single set. And it turns out that that is a set itself, and it is an ordinal as well. It's you can give an order on that set, and that order has the property you want. It's well-founded. And so it's kind of a swindle, right? You have this trivial construction that gives you this incredibly large and powerful object.
So does this? So the you're saying that this is the set of all subsets of the natural numbers is an ordinal that is bigger than
Of
that.
no, it's the set of all subset of the natural numbers which happen to be ordinals, which happen to have the structure of an ordinal.
Right, and it's not the same structure as the reals. It's a different structure of the reals because it doesn't.
It's a different structure as the reals, and the order is very different, right? The order on that set doesn't have anything to do with the order structure of the reals.
Right.
And it's well founded. I mean, that's it's a simple theorem, but it requires a little bit more work than I can really do over a podcast.
That's that's really cool. And since we're touching in this topic as well, it also brings to my mind the problem of the millennium, which is now finding the set in between the naturals and the superset of the naturals.
So you can certainly, so it was well known at the time people came up with this. This is certainly a set that has larger cardinality than than the natural numbers, but it's not clear that it has the same cardinality as the real numbers, and that has to do with this Hilbert problem. But it certainly has bigger cardinality than natural numbers, and it certainly is this crazy huge set that's almost impossible to imagine. And my point is, this set gives you the ability to build fixed point theorems, and it gives you the ability to prove consistency of all these different logical systems. And basically, you have to have this kind of impredicativity, this ability to talk about arbitrary subsets of a set to construct, right? And so in predicative theories, you just don't have this giant uncountable ordinal. You need to build ordinals really explicitly from the ground up.
That's very interesting. That's pretty cool. What about when we're talking about impredicativity in terms of theorem provers? Because there is a big debate of whether we can use set in sets or there's an impredicative flag in Coq as well, something like that. How does that play a role here?
Right. So like I said, there are these inconsistent systems, and one such system was the original system Martin Luff came up with in 1971 or 1972, and again, this was almost a century after Frege, but at the time he conceived of it, it wasn't obvious that it was subject to this self-reference problem. But pretty quickly after that, it turned out that the ability to, quantify over types, take the set of all types, or for all alpha type, alpha. Sorry, I'm confusing two notions. Sorry, saying that type is of type. It's not obvious that this created a problem. It's certainly impredicative, right? Because you're saying that type, a type can be defined in terms of type itself. But again, it wasn't obvious that this was going to be a problem, right? Because you have some different kinds of impredicativity, right? You have the innocent kind and the guilty kind, or what Torsten Altenkirch would call the honest kind, which is the inconsistent kind, and the dishonest kind, which is the consistent kind, right? He thinks impredicative systems are more honest when they're inconsistent. And so it turned out that this was inconsistent. It turns out that if type is in type, then that's really inconsistent. What's a little bit surprising is if you say, okay, type isn't in type is in this other second thing. Typically it's called box or kind or something else. But you allow this large quantifier, which says I can quantify over every type, right? I can say for all x or for all t of type, I have a function from t to t. Okay, this is still impredicative in some sense, right? It's basically saying I'm building a new type by quantifying, by taking the product over all possible types. All right, and it turns out that type and type is inconsistent, but taking these big products, these big fralls over all types and building a new type out of that is not inconsistent. But the proof of consistency is subtle. It's quite subtle. Girard actually worked this out after also finding the contradiction with Martin Luff type theory. And it involves set theory itself, right? So you really need to use kind of the impredicative power of set theory to prove consistency of these systems. And it's also a subtle consistency. There are things you can add, right? If you have this big pie, this big quantifier over types, there are a lot of things you can add that look kind of innocent and that end up being inconsistent, right? And I can talk about this at length, but I'll just say that it's consistent, but it is subtle. And so in particular, in Coq, right, you have this kind of big quantifier over prop, but prop is carefully crafted so that it is at least as consistent as Zermelo's set theory, right? So they're roughly at the same level of consistency. They're both impredicative, but they're both consistent. And if you add this option in predicative set, you're adding the second thing, this impredicative quantification over sets. And that is much more doubtful whether it's consistent or not. It's a much more dangerous thing because there's no obvious way to relate the consistency of that thing to just normal set theory. It becomes a different thing. And so, and so all these things are a little bit scary, right? People find these crazy contradictions in them. So what Martin Luff did was, okay, this is crazy. Actually, impredicativity is bad. So let's build a predicative system and let's try to use that to formalize mathematics. So he basically, took the same path as Russell, where he was like, okay, well, let's be predicative and let's be honest. Let's use systems that are pretty clearly consistent. And so, basically these two schools, right, where the French had Girard, who managed to show consistency of this impredicative system, and Cocon at the time, and the Swedish school with Martin Luff that was like, okay, well, let's forget about these impredicative systems. They're too scary, and let's work with predicative systems. What I find kind of funny is then Cocon moved to Sweden. He worked on Agda, and he basically founded the French school of impredicative systems, but eventually he ended up doing most of his work in this Swedish school. I call them the French and the Swedish school, but that's a simplification, right?
Right.
Researchers from all over the world
have
worked on these different theories. So basically, there are three things. There are the inconsistent systems, or four things, right? The inconsistent systems that we know are inconsistent. The systems which we believe to be consistent, but are really scary, like in predicative set. The systems we believe to be consistent, but are still a little bit scary, like set theory and normal vanilla Coq. And I have to say, Isabelle is also kind of in this category. It's a little bit weaker than Coq, but roughly in the same category. And then the very weak systems like Agda or 12, and that we're very confident are consistent, but are much less powerful, and so are maybe a little bit more awkward to formalize mathematics in, right? And so we have this scale, the sliding scale of philosophical scariness of the system.
Wait, so you think that you're saying that Agda is less powerful than Coq? I didn't know that.
Yes, in the meta theoretical sense. Coq can definitely prove consistency of Agda if you work very hard.
I don't see that
because it doesn't have that big quantifier. It doesn't have that prop where you can say for all t of type, then you build some proposition that depends on t, and that is again a proposition, right?
Oh, I see. So because of prop.
Yes, because of prop. Yes.
Oh, right. Interesting. I never thought about that.
It's a subtle point, and I think working out the details is this kind of folklore theorem that I'm not sure has ever been published. But yeah, Coq is definitely, more powerful, for fundamental reasons than Agda. And actually so is Isabelle again.
But yeah, I can see that. Prop is actually a pretty good idea also in the proof engineering aspect, in the sense of you're going to use prop when you're doing proofs and you don't care about running your program. So we're going to throw all that away to keep things, to make sure that things are consistent. It also kind of comes back to this idea that you were talking about on, I believe you're talking about Girard's system, which was the same system as System F, right? What was the name that he gave to it?
I think it was System F.
System F was Reynolds' version, right? It was the same system in the end, but Girard gave it another name, if I'm not mistaken.
I would have guessed Girard called it System F, and then Reynolds called it something else, but I'm actually not sure.
Anyways, in any case, it's the same system, and at the end of the day, it's System F, right? And you were saying that in the System F, You have the big lambda, which you can quantify, well, the big pi, right? The big pi, which you can quantify over all the types that are in box. And the box are, and because of this subtle stratification, you can still get consistency, but it's subtle, but
Yes,
it makes
fragile. It's fragile
right.
consistency. So there's this, yeah. So yeah, how to say this? There's a subtle distinction where if you want to interpret um, system F as just a schema for realizers, it's roughly, yeah, it's this kind of weak set theory, right? So it's stronger than AGDA, but it's this weak set theory. But if you really want to interpret system F quantification as being really about sets, right? That pi is an actual product, and the arrow is actually the function space. Then you can't interpret this into classical sets, right? There is no way to build, the product of all sets in classical logic, right? So so there's this subtle point where if you want to interpret system F and show consistency, you need to interpret the arrow as this kind of implication and this big product as a kind of big intersection. And there you can prove consistency relatively easily with this relatively weak set theory, roughly, second order arithmetic. But if you want to interpret it as actual functions in an actual function space, there's no way to interpret that consistently into sets if you have classical logic.
What do you mean here
That's
by this
inconsistent.
interpretation that we were talking about? What's the idea of this proof that you're just catching in our minds here?
The consistency proof or the
Yeah,
inconsistency proof? Oh,
the
the
consistency
consistency
one. You're
proof.
saying something along the lines of interpretation and bringing it to set
Yeah,
theory
yeah,
so
yeah.
that we. Mhm.
So, yeah, so this kind of interpretation of system F is basically you want to interpret types as predicates, as sets of natural numbers. So each type is going to be a set of natural numbers. And then the arrow type is not quite inclusion, but this kind of inclusion where you say, okay, well, um, you know, if you have the interpretation of a type, which is a set of natural numbers, then, if you look at a natural number as the code of a function, then the the interpretation of like A arrow B is going to be all the numbers which are codes of programs that send things that are in the first set to things that are in the second set. All right. So it's kind of like inclusion like operator. And then you interpret pi, that big system F pi, as intersection. Okay. And now you've built this interpretation of system F as every type in system F becomes a set of natural numbers. And this basically, it shows consistency of system F. It shows that you can't interpret the empty type, right? And it's a very useful interpretation of system F. Basically, there's this very strong correspondence between sets of natural numbers and system F types. And that
Gotcha.
correspondence is what I would call the Reynolds correspondence.
Okay.
And
Okay.
it's,
So we're translating the problem to set theory here, so that in set
yes,
theory you have the tools necessary to reason about what you want.
right.
Mm-hmm.
Yes. So you're not interpreting, again, the arrow is function space, and you're not interpreting the pi or the for all as a big product. You're interpreting them as something different, but it does still talk about sets of natural numbers and operations on those sets. And yeah, and this is a useful rule of thumb. But if you really insist on interpreting the pi as the product of all sets, and if you really insist on interpreting the arrow as the function space, then there is no way to interpret system F in those terms in classical logic in a way that is consistent. Yeah, what's a little bit bemusing, what's a little bit surprising, is that you can interpret it in intuitionistic set theory. So this is kind of the bridge between the things I want to talk about, which is this crazy thing happens where this like impossible product over all sets is actually consistent if you just give up the excluded middle, right? So the excluded middle here is actually harmful to interpreting all these crazy things like this big product. And yeah, but it's still kind of crazy having this big product over all sets. But there are intuitionistic set theories where you can talk about sets and you can talk about subsets and you can do all the set theory stuff you normally do without the excluded middle. So you can't, say, a or not A. You can't say an element is in a set or an element is not in the set. You can't prove that. And these set theories actually are consistent with this system F interpretation, where you can say, well, take the product of all sets.
I see. So if we translate into a set theory that does not have excluded middle, then we have consistency.
Yeah, a miracle occurs and you can actually make that consistent, right? But then you're on thin ice, right? Any additional axiom you add is almost surely going to make you inconsistent, which is why in Coq, impredicative set is so dangerous, right? Impredicative set is exactly this kind of set theory, right? It's a type theory, but it's basically that, what I've described. And so if you add excluded middle to impredicative set, that's inconsistent.
Oh, okay. Is that a hard proof?
It's a short proof, but it's a hard one, yes.
Okay. Just getting a sense if it would be able to do a sketch of it.
I can do a sketch of it. Basically, you want to say, okay, well, system F doesn't have any models in set theory. What you're going to do is you're going to build a system F type, which as a set cannot possibly exist. And what you're going to do is you're going to take the set with two elements. All right. So it has to be a set with at least two elements, right? Because otherwise you're in prop, right? Prop is basically all the sets that have at most one element. So you take the set with two elements, you take the product over all types X of the set X arrow 2, arrow 2. So 2 to the 2 to the X in some sense. Does that make sense, that set I've defined? So you take the big product over all X of 2 to the 2 to the X as sets, right? Where exponentiation is the space of all functions. Yeah.
Right. And 2 is the same as bool.
Yeah. It's a set with two elements.
Right.
All right. Well, it turns out, so in system F, you can definitely build that big product. And in set theory, you can examine what this big product must be. And you can show that set has to basically have some really nice properties. And in particular, it has to be isomorphic to itself, but 2 to the 2 to the itself, right? So the resulting set S has to be isomorphic to 2 to the 2 to the S, all right? So that's a thing you can prove, right? And that's true regardless of whether you're in intuitionistic or classical set theory. But if you're in classical set theory, you're in trouble because those two sets must have different sizes. And at some point, you're going to crucially use the excluded middle to show that they have different sizes. And and there you have your contradiction with the excluded middle. So in intuitionistic set theory, like this crazy things happen where you have this huge set, this isomorphic to a much smaller set, but you can't prove that they have different sizes. For all you know, they could be isomorphic. And this is definitely, if you talk about this with Andrej or you talk about this with Martin Escardo, they're going to tell you all about these crazy worlds in which you can have this big function space that happens to just be countable, right? And but it's subtle. It's a subtle thing because if you take the set of all functions from nat to nat, say, that you cannot assume to be countable.
Why not?
Because the original diagonalization proof is actually going to work even in an intuitionistic setting, right? So if you assume that nat arrow nat is isomorphic to nat, right? There's really a bijection with the natural numbers. Then you can just carry out that diagonalization proof. You can just you can take, the function that looks at its own code and sends it to itself and applies it to itself plus one, right? And that
Gotcha.
function is going to exist, but it can't possibly exist. So
Right.
that proof goes through just fine. But if you take the apparently much bigger set, right? Nat arrow nat, that function space, arrow nat, right? So you have this sort of extra indirection. So you have a function that takes a function from nat to nat and it returns a natural number. That, for all you know, could be countable, right? And it's consistent to assume that in intuitionistic set theory. So this kind of like extra indirection, this extra function space now brings you back into the countable world. And I think, again, Andrej talks about this, but this is kind of exciting, right? You're in this crazy world of like sets that don't behave at all like you thought sets would behave. And so I'm kind of dovetailing here, but my point is that this crazy impredicative world can be consistent. It's a little bit fragile philosophically. It's not necessarily grounded, but it opens up the realm of like fascinating things where you can look at these intuitionistic theories with these big products and these crazy function spaces, and those end up being at least consistent with normal mathematics, normal set theory. And so it's kind of exciting to explore that, even though philosophically it's a little bit more nerve wracking to be at the strength of these impredicative theories.
Right. Right. So okay, we're talking now about excluded middle
Mm-hmm.
and and how it relates to consistency of these theories. And we've seen a couple of things that you have mentioned. Is there any? What are the other interesting aspects that we can relate to excluded middle? I remember that there is some idea that relates excluded middle with CPS transformation.
Right, right. So far we've talked about predicativity versus impredicativity, and really I was saying, okay, a predicative system is going to be much weaker and much more likely to be consistent than an impredicative one. At the time people were kind of working these things out, they were also asking similar questions about the excluded middle, right? Because in the same way that an impredicative definition is kind of scary because it doesn't give you this explicit construction, um, it feels like the excluded middle has a similar problem, right? You can prove that things exist with the excluded middle without actually giving an example of that thing, right? You can prove abstractly that some things exist just by assuming that it doesn't exist and getting a contradiction, right? And that's this double negation thing, um, where if you assume something exists and you get a contradiction, you can apply double negation and you conclude that that thing actually must exist. Okay, but you don't actually have an example in your hand, right? The proof is just like this crazy assumption followed by a contradiction. So it wasn't obvious that this principle was at all, you know, good, right? It wasn't clear that it was consistent to have this excluded middle. Mathematicians, of course, used it all the time for
Yeah.
a ton of things.
Right.
So they weren't really willing to give it up. But at the same time, these logicians were looking at it and saying, well, for the same reason we don't like impredicativity, we're not super crazy about the excluded middle. But again, Gödel came in and he was like, oh, wait, actually, Gödel and others, I think Brouwer and Komorogov, were like, okay, wait a minute. Actually, okay, it's not inconsistent to assume the excluded middle. And the reason for that is that there is a translation, a very simple, very constructive syntactic translation from a system that has the excluded middle to a system that doesn't have the excluded middle. And that translation preserves consistency, right? So if you had a contradiction with the excluded middle, you'd also get a contradiction in this world without the excluded middle. And that translation is usually called the Gödel translation or the Gödel-Gensen translation.
How do you do this translation preserving consistency? What's the idea?
That's a good question. So what's the idea? Basically, the problematic elements of non-constructive logic, classical logic, are the exist construct and the or construct. Okay. What is true intuitionistically, though, is let's see. I'm sorry. I'm thinking how to explain this. So A or not A is not always true intuitionistically, right? It's not a theorem of intuitionistic logic. If you have some arbitrary proposition A, you can't prove A or not A. That's not consistent. What you can prove is not A or not A. Right? That is actually a theorem of intuitionistic logic.
Mm-hmm.
Does that make sense?
Yeah.
So it's kind of surprising, but adding two negations right in front of that disjunction all of a sudden turns it into a theorem in intuitionistic logic. Okay? And so that's the crucial insight. It turns out that if you take your classical proposition that's provable, it might not be provable in intuitionistic logic, but adding double negations at carefully chosen spots inside that thing turns it into a new proposition, which happens to be provable in intuitionistic logic.
Right? I see.
So you take your thing and you add not in different places. You add not, and you end up with a new theorem, which doesn't mean the same thing intuitionistically, right? Instead of proving that something is true, you've proven that it's not contradictory, right? Which is, I always say it's like if you're in a closed room without any windows and you can't hear outside, right? Say you're a grad student and somebody tells you it's raining, you can't prove that that's not true, right? It might as well be raining outside.
Right.
And that's definitely not the same as being outside and feeling the rain on your face.
Mm-hmm.
But, it's something. And so this translation is basically the Gödel translation.
Gotcha.
You add nots everywhere. And the insight is that if you can prove false, the translation is going to be not false. But it turns out that intuitionistically, that actually is equivalent to false, right? So if you could prove in classical logic false, then you'd be able to prove not false in intuitionistic logic, and you'd also be able to prove false, right? So basically, I'm taking, a problem in classical logic, I'm turning it into another problem in intuitionistic logic that is equivalent to false. And so now you can go backwards and say, oh, if I could have proven false in classical logic, I would also be able to prove false in intuitionistic logic. And therefore, there's no reason not to trust the consistency, at least, of classical logic. You can object to it philosophically. You can say, well, it's stupid that I can prove that something exists, even though I don't have any concrete examples. But you can't say, oh, classical logic might not even be consistent. Because of this translation, that it's at least as consistent as the intuitionistic one. So that's the idea of the translation. I haven't explained how it relates to continuation passing style, to be honest. I can try to do that. In some sense, let's see. In some sense, the double negation of something can be seen as a continuation of that thing, right? So instead of returning an A, you say, I'm going to return something that if you give me a function that takes in an a, I will be able to keep computing with that function, right?
Right, right, right.
So you're saying if instead of giving me an a, instead of giving you an a, I'm going to give you something such that if you give me a function that takes in an a and returns false, I will give you false. All right, and that's exactly the double negation of a. And returning false is really like the best you can do, right? False is this like magical thing, right? It's basically subsumes all the other types. And so really, in some sense, it's saying if you give me something that if you take in an A, it can give you anything back, any B. So for all B, you have an A arrow B, then I can give you a B. So for any B you ask for, if you give me a function that takes in an A and returns a B, I can give you a B. All right.
Right,
And that's
right, 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 right.
exactly continuation for A. And so what's fascinating in my opinion is people did not notice this right away. people, Gödel, and Gensen, they build this translation. Kolmogorov also had this translation called the A translation. And it worked fine, and it was very useful for logicians because it was like, okay, here's a system that's classical, here's a system that's intuitionistic, here are theorems that relate the two that use these translations. And then on the other side, completely independently, a bunch of programmers were like, oh, it'd be really nice if like instead of returning an A here, I could sort of wait and only, do something with a continuation. And at some point, somebody was like, hey, what happens if you try to give types to these crazy programs? And I actually don't know if this story is true, but somebody told me, and then somebody went across the hallway to their colleague, and they were like, hey, here's the type of call CC, right? So this kind of continuation operator. And that person took one look and said, that cannot possibly be the type of call CC because that's not an intuitionistic theorem. If you translate it into logic, it's not an intuitionistic theorem.
Right.
It's a well-known classical theorem. And so because programs can be interpreted as proofs in intuitionistic logic, this can't be a program. And actually, yes, it could. It's just this is the secret ingredient of like turning classical logic into intuitionistic logic. So it's kind of like a beautiful thing, right?
Yeah.
This completely independent discovery of the same technique.
The first time I heard about this technique of transforming classical logic into intuitionistic logic and therefore classical proofs into programs, right? In a way, I was very surprised because I was under the impression that, well, there is the bijection, right? Like there is this bijection between intuitionistic logic and programs, and that's not necessarily true in classical logic, but that's not quite the case because of CPS transformation. And with
Right.
CPS transformation is exactly the ingredient that was missing. So excluded middle is not actually the problem for translating proofs to programs, right?
Yeah, in some sense. It depends what you want out of that translation, right?
What do you mean?
It's if you want, right? So it, one of the beauty kind of this proofs as programs paradigm is that it gives you, if you give me a proof of something, I have a program and I can run that program and it's going to have certain properties, and depending on the properties you ask, that might be true about intuitionistic logic, and it's not going to be true about classical logic anymore, right? So if I have a proof of A or B in intuitionistic logic, and I extract the program that corresponds to that proof, and I run it, then it's at the end of the day, once it's finished running, and it will finish running, right, because of this normalization argument, it will give me either, left of a proof of A, or right and a proof of B, right? It's going to give me one of those two things, right? But that's not true if you have this call CC translate. If you have this CPS translation of a classical proof, right? If you
I
take a
see.
classical proof of A or B and you extract the program, that's associated with that, and you run it, you don't know what you're going to get, and it's probably not going to be either proof of A or proof of B. It's going to be something that's kind of expecting a continuation.
I see. I see. Like something like if you give me an A, say, then I can give you the answer.
Exactly. Yeah. Yeah. So I learned about this years ago. I don't claim to understand this perfectly, but I learned about this years ago, but with Alexandre Miquel, who is like kind of he explained it as a devil's bargain, right? You want to
Right.
you want a program that realizes the excluded middle,
Uh
and the devil comes and he says, "Oh yeah, I'll give you a program that realizes the excluded middle.
Right.
You just need to give me, the excluded middle is this like it's a choice, right? You either get one wish or you get this suitcase full of $1 million, and yeah, the call CC is going to allow you to time travel back, right? So the proof of A or not A is always going to be like, oh, it's actually not A, except I need a continuation that gives me that A, right?
Right.
And so when you try to invoke that, right, to get your contradiction, right, so the call CC is giving you, yeah, I'm sorry, the proof of excluded middle is giving you back a proof of not A, and you say, okay, well, a proof of not A is something that takes in an A and gives me false. And if ever at some point you have an A, you can say, okay, well, now give me my proof of false. Well, what call CC is going to do is basically travel back to time for when you ask for that proof of A or not A.
Yeah.
Take the A you gave it and go back and say, oh, actually, yeah, it was an A. It was an A. It was a proof of A all along. So yeah, so this is kind of a swindle, right? It's kind of a lie to say that, yeah, you're giving a proof of A or not A. What you're actually doing is a little bit more complicated, right? You're giving a program that's sort of somehow going to behave in a certain way, but not the way you would expect for a disjunction. And so that really is the crux, right? If you say proofs as programs and you expect, a proof of a disjunction is going to reduce to one of the two, then no, classical proofs are not programs. If you expect something a little bit softer, a little bit more interactive, then yes, there's a whole field of computer science that thinks about these classical proofs as programs. And yeah, I don't know. This is kind of a fun game to play. I think it's a very yeah, I think it's this very fruitful field where you can kind of think about what logicians know about logic and what computer scientists know about continuation passing and effects, and you try to marry the two philosophies.
Mhm. It's very fascinating to me, excluded middle and all of these ideas on how computer science ties back to logic and provability, right? And proofs. And there's actually one more thing that also kind of relates to excluded middle. Maybe you can give us some sort of some light on this, because every time that I'm studying logic, there is this one particular kind of rule that pops up, and it's not quite clear. Like every time that I'm reading about this, apparently this idea of cut elimination adds a lot of power to our system, and it's not quite clear to me why, or why is it interesting, or why does it relate to things here? How does it relate with excluded middle? What's cut elimination?
Yeah, I mean, how much time do you have?
We have plenty of time, so yeah.
Yeah, it's an interesting question. Yeah, of course, I'm fascinated by this question. because, it relates to these ideas of termination and consistency that I'm really excited about. So I think, I think the original formulation of cut. So again, it's kind of historical context, because that's a lot of how I interpret things. So in the original context, again, people came up with these complicated logics and these complicated meta theorems. And Gensen was coming in and he was trying to do the same thing, but he had this very structuralist mind, very algebraic, and he was trying to build a very simple way of understanding the rules of logic. So at the time, logic was complicated, and writing down the rules of logic was complicated. And there's kind of magical aspect where some of the logical rules seemed just a little bit pulled out of a hat. So he gave this very simple deduction system that where all the rules were kind of intuitive, and he called it natural deduction because he was like, okay, I found this natural formulation of logic. And unfortunately, he was having a hard time proving any of the meta theorems he wanted to prove about it. One of them was consistency. So he designed this different system, and I'm simplifying a little. He designed a series of systems, but he designed a second system which he showed could prove the same things, but also he knew how to prove meta theorems about that system. And that system was the sequent calculus. And so the sequent calculus has this kind of nice structural shape. And it turns out that in the sequent calculus, one of the rules is called cut. And that cut rule is basically a very intuitive rule. It says if, assuming A, you can prove B, and assuming B, you can prove C, then assuming A, you can prove C. All right? This is very simple. And the assuming is really assuming, right? It's on the left of the sequence, right? So something I've found people have a little bit of difficulty understanding at first is the difference between implication and this turnstile, the sequent. Implication is really a logical way of saying if A then B, and the sequent is the logic way of saying I have a bunch of assumptions and I'm trying to prove a bunch of conclusions. And so the way the logic is formulated is about the sequence, and then each of the individual things in the sequence might have an implication in it. But in some sense, the sequence symbol is meta implication, right?
Right.
All right.
Right.
Great. So I've talked about the cut rule. I said, basically it's assume A, prove B, assume B, prove C, then assume A, prove C. Now, it turns out that you don't actually need this rule, right? You can sort of directly, in the sequent calculus, prove everything without this rule, but it's very hard. In particular, you're usually going to need a lot more steps to get from A to C directly without this kind of B intermediary, because you're going to have to do kind of all those operations that you need to get B and all those operations that you need to get C. You need to kind of interleave them. And so proving that theorem, which is the cut elimination theorem, proving that you don't ever actually need the cut to carry out your proof, turns out to be quite hard and require a very subtle induction. Okay, so why prove that thing? Because it turns out that the system without cut has all these fantastic properties. In particular, it becomes trivial to prove that the system is consistent, because without cut, every rule basically doesn't have any fresh variables, above the dividing line. And what does that mean? It means it doesn't really introduce any new propositions, any new variables that you don't know anything about, right? In the cut rule, there's that B that comes out of nowhere, right? In the conclusion, you have A, from A deduce C, but above that line, you have this new B that comes out of nowhere that you don't know anything about. It could be much more complicated than A. It could be much more complicated than C. In the system without cut, you just don't have any of that. And in particular, you can just look at all the rules and say, okay, which one of these would allow me to prove false in the empty context? And there are just none that apply. Just 0 rules apply. In the system with cut, you have no idea, right? C could be, you could come up with some magical B, and then the empty sequence proves that magical B, and then that magical B proves false, and then you have a proof of false. But without cut, you don't have any of that. Nothing complicated happens. And there's a second property that's like the subterm property, where basically if you're in propositional logic, you can show that, if you can deduce C from A, you can do that using a proof that doesn't introduce anything that doesn't appear in A or C. Basically, every step of the proof is only going to contain sub propositions of A and C. So this is all trivial if you don't have the cut rule. It's really very simple. And so cut elimination goes from a system that's actually kind of usable to a system that has these magical, very simple properties. And so basically all of the interesting stuff happens in this cut elimination theorem, where you say, okay, well, if I'm going to eliminate cut, I really need to understand the structural properties of my system. And okay, great. So this is a very roundabout way of coming to the answer to your question. What does this have to do with computation, right? So how does the proof of cut elimination go, right? You have a proof from A to B, and you have a proof from B to C, and now you need to build somehow a proof from A to C. Well, you're going to reason by cases here all over the place. You're going to look at all the ways you could have proven B. Look at all the cases there. You're going to look at all the ways you could have proven C. And basically, you're going to fiddle to get directly a proof of C without that intermediate cut step. And this, if you look at sequent calculus and you try to apply the proof of programs paradigm, you can build this very strange programming language that basically associates a proof with each of, associates a program with each proof. And then you can say, oh, well, cut is actually a step. Each cut reduction, each step in that proof of cut elimination is actually a computation step in this language.
A beta reduction?
Well, not quite, right? It's not going to look like a beta reduction. It's going to look like something more complicated. But it's going to subsume things like beta reductions.
Okay.
So in the sequent calculus, there's just one big computation rule, and this cut elimination. In natural deduction, it turns out you can't do this you can't just eliminate a single rule. You have to be a little bit more complicated. You have to eliminate kind of combinations of rules. In the natural deduction, you have intro rules that introduce operations like implies or disjunction. And then you have elimination rules, which are rules that, above the line you have that operation, and below the line you don't have it anymore. And then in natural deduction, you could say, okay, well, an intro rule followed by an LEM rule, you could actually just short circuit that and just not have either. And those rules look a lot more like the classical beta reduction rules or the classical computation rules you have in programming languages. And there, natural deduction is much more suited to talk about intuitionistic logic. And it's much more suited to, just have this kind of very natural proofs as programs environment. But you don't have a cut rule. And so, and so when people talk about cut elimination, usually they're talking about this more complicated system, or at least a system that's less amenable to the proofs as programs kind of interpretation. But at the same time, it's kind of inspirational because, logicians have studied cut for decades, and it turns out that these these systems, these sequent calculus systems, are very naturally classical. In fact, it's hard to have sequent calculi that aren't classical. And you don't even need to assume explicitly the excluded middle. You just sort of have that for free in the sequent calculus. And so now you're in the system where if you can come up with programs that correspond to the proofs, you're going to have a very natural, CPS, explicit stack versus programs environment. And so you can kind of get insights into what a programming language with explicit notions of stacks and continuations is going to be just by looking at classical logic, theorems.
That's very interesting. It's very interesting. Yeah, cut elimination. You bring me memories when I was watching some classes on a summer school showing what is cut elimination, and it's just so beautiful. It's so beautiful. It's definitely worth reading more about it and diving just into that.
I'm going to confess, I prefer natural deduction. I feel like at the time of Gensen, cut was kind of this important rule, and there's something kind of beautiful. But if somebody can show me a natural deduction system that captures, the same proofs as the sequent calculus, I much prefer working with that natural deduction system.
Right. I think in the context of the summer school, there were some, because in natural, as you were mentioning at the beginning, he came up with natural deduction to prove some meta theory of sequent calculus, right?
Yeah, it's
or the other way around. The other way around.
The natural deduction is the thing you want to work in.
Yeah, exactly. And because it's nice.
Calculus is the thing you want to prove things about, right?
So one is very, very good for reasoning, and the other one is very good for using. Right?
Yeah.
That's
exactly.
Pretty good. That's pretty good. So another topic that I had here is related to realizability proofs. What did you have in mind here? Did we touch on this topic yet?
Yeah, I mean, not as much as I like. I really like realizability. So,
what is realizability?
So in a way, it's a way to associate programs with proofs. And so it's very related to what we've been talking about. Again, what's kind of funny is people discovered this independently of the proofs as programs paradigm without realizing that really they'd rediscovered, the same concept. So at the time, people were trying to understand intuitionistic logic. And in particular, I've said all these things about how, in intuitionistic logic, if you have a proof of A or B, then really you do have either a proof of A or a proof of B. But I haven't really explained how you prove that, right? I just said it was true. But proving it is not obvious, right? So it's actually not obvious how you get from a proof of A or B to, a proof of A or a proof of B. And to prove that theorem, right, that meta theorem, again, you sort of have to jump through some hoops. And so what you end up doing is you examine the proposition and you turn it into something that has kind of programs associated to it in a kind of like more or less kind of clear way, and then those programs are going to end up computing and giving you some information, and really it's very similar to what we talked about with cut elimination, but it kind of forgets a little bit more information. It's the same process, but it just removes all the non-essentials. So essentially, you're just going to keep the information about existentials and disjunctions, and then everything else you're sort of going to like paper over. And so there's this very this very clear transformation that I think I'm actually not going to say who it's due to because I'm almost surely going to get it wrong, but I want to say Aaron Hayting. And again, Kolmogorov, where they just basically took intuitionistic arithmetic and they were like, okay, well, now we need to know that actually, we can get this existence property and we can get this disjunction property. And they were like, okay, well, what we're going to do is we're going to transform the proposition, and implication is going to be that thing I mentioned earlier, where it's like we're going to take a program associated to A, and a proof of implication is going to become a program that takes in whatever is associated with A and returns a thing that's associated with B. And a proof of disjunction is going to be a thing that either computes and returns a proof of A, or computes and returns a proof of B. And a proof of conjunction is going to be a thing that computes and returns a pair of proofs. And you build that interpretation where you say, okay, well, each proposition is going to become a set of programs, right? And remember when we were talking about system F way earlier, I was saying you take a system F type, and you return a set of natural numbers. It's the same thing. It's the same transformation, except it's programs instead of natural numbers. But of course, you can code programs as natural numbers, and people were doing this, ever since Gödel. It was a very kind of common thing. And and you do that, and you end up with kind of an interpretation where each logical proposition becomes a potential set of programs. If you can find a program that's in that interpretation, basically you've realized the proposition, right? And then the big theorem is if you can prove it, if you can prove a proposition P, then actually you can build a realizer program for P. And that gives you all sorts of meta-theoretical properties. In particular, it gives you that disjunction property, it gives you the existence property, it gives you consistency, it gives you a whole bunch of things.
Disjunction and existential property? What does that
mean? The disjunction property is if you can prove A or B, then actually you can get a proof of A or
the proof of B. Oh, I see.
And if you can prove that there exists X such that P, then you can actually find a numeral that P that satisfies P. You can actually somehow compute and get that numeral.
Right. So you're saying that the realizability here is kind of saying that
in the same
way you have the program,
that,
you can run your proof,
in the same way that Gensen transformed these natural deduction proofs into sequent calculus proofs to be able to prove meta-theorems. This is a similar transformation. You take natural deduction, but intuitionistic, you transform it into statements about programs. Right. And then you prove that, this meta-theorem, that if, something is provable, then you can get a program in that interpretation. And then you get all these meta-theoretical properties very easily, just like with the cut elimination property. And and so this was kind of exciting. It was a very clear justification for why intuitionistic logic was correct in some sense. Otherwise, if you don't have the excluded middle, but you still can't prove that, the existence property. You can't prove that if I prove exists X such that P, then there actually is an X, right? That I can write down. Then you have nothing, right? It doesn't, you haven't really gained anything from removing that axiom, and so you might as well keep the axiom. But no, this realizability interpretation gives you the meta-theoretical properties of intuitionistic logic that you actually care about. And it comes with a whole host of fascinating properties, right? You can really use this realizability interpretation to prove all sorts of things. So anytime somebody has an interpretation, and this comes back to way, way early when you're talking about models, every time you have an interpretation that you can use to prove consistency, you can use it for all sorts of things. You can ask, okay, well, this interpretation, what can it allow me to prove the consistency of, right? And you add axioms and you say, okay, well, this interpretation would work with this axiom and it works with that axiom. And therefore, all these things are consistent. And one of my favorite axioms is the church thesis axiom, where you can sort of take intuitionistic arithmetic, with function spaces, and you can just say, oh, every function in the function space is actually computable, right? Actually, every function that I can name from nat to nat is actually can be computed with some Turing machine, right? And this is kind of crazy. I mean, in classical mathematics, this is extremely false, right? You can even prove that it's false, right? In classical mathematics, you can easily define a function that's not computable by a Turing machine. And that's almost like the first thing Turing proved, right? Is that there are functions that Turing machines can't compute. But in intuitionistic logic, you can assume that this is true. You can assume that there are no such functions. And realizability realizes that axiom. So it shows that assuming that axiom is actually consistent, which is quite fascinating in my opinion. So it's consistent to live in a world where every function is computable in mathematics if you don't have the excluded middle.
That's very interesting.
Yeah, and something that I find even more interesting is again, just because something is true from the outside doesn't mean it's true if you assume it from the inside, right? So it's still you know, like I said, the in intuitionistic set theory, the set of subsets of natural numbers is not countable, and you can actually prove that. You can prove that internally there's no bijection between the set of subsets of the natural numbers and the natural numbers. Okay, but from the outside, that's true, right? It's true that there's only a countable number of subsets of the natural numbers because your whole language is countable. There, you can't even write something that's uncountable. You can't even write an uncountable number of things, right? There's only a countable number of subsets that you could possibly name. So this is something that's true from the outside that can't possibly be true if you assume it from the inside. And it sounds very similar to that thing that I just said we assumed, which is that every function from natural numbers to natural numbers is computable by some Turing machine, right? Because Turing machines are certainly countable. There's certainly only, a countable infinity of them. And the functions of natural numbers to natural numbers sure seems like it's the set of subsets of the natural numbers, but it's consistent to assume that they're all computable. So these two very similar things, one is inconsistent, the other one is consistent. And the way you prove that is through this lens of realizability. What can you realize? What can you turn into a program that explains why it's true? And that's exciting to me. I think it's really fascinating, right? You're in this world that's completely different from classical mathematics, and you're also in this world where you're looking at things from the outside of the logic, and then you're trying to get them in the inside of the logic. And I find that there's something very compelling about this whole approach, which is we as mathematicians and as people, we're trying to understand what's true about us and about our practice and about what we know about the world, right? We're trying to, as a system of of knowledge, we're trying to gain knowledge about ourselves and about the environment we live in. And logic, of course, is a tiny little corner of that. But it's interesting to see systems and say, okay, what can this system know about itself, right? And intuitionistic logics can know about themselves that they only have computable functions. And, there are a lot of things like that you can assume internally or externally. And there are things that are true externally that you can't assume at the same time, right? Like you can know that there are computable functions, and certainly consistent to assume that, the excluded middle holds, right? And if you're a classical mathematician, you believe that the excluded middle holds, right? You believe that everything is either true or not true. But you can't assume those two things internally at the same time. So yeah, I don't know. This is exciting, and I have a last point about this. And one thing that puts off mathematicians, I think, is that this seems very divorced from their reality, right? If you say, oh well, in intuitionistic math, all functions, it's consistent that all functions are computable, they're going to be like, this is ridiculous. Like, why should I ever care about a system that's just so contrary to my intuition, right? My intuition is that there are all these functions, and they're all like way more functions than there are Turing machines. And, you know, I'm fine working in this realm of mathematics. You know, I've done it for however many years, and I don't want to just destroy all my intuitions, right? Telling them something that's very counterintuitive isn't going to convince mathematicians to care about intuitionistic logic. I think it might convince undergrads. Certainly for me, it's very exciting, these counterintuitive things. But to mathematicians, I think having these counterintuitive things isn't very compelling, right? They're already used to the things they're used to. So here's the argument for mathematicians. There is an interpretation for intuitionistic set theory in any topos. So what's a topos? Well, it's a category theoretical concept. It's basically a set of axioms for some abstract structure that has a bunch of, various properties. But what's fascinating is they appear everywhere. They appear everywhere in mathematics. They appear in algebraic geometry. They appear in algebraic topology. They appear, in an analysis. They really appear. They appear in complex analysis. They I think appear in analysis. So it's this very common thing, and it's basically, yeah, it's a mathematical universe, right? It's called a topos because originally it was talking about sheaves over a topological space. So it doesn't really matter what a sheaf is, and it doesn't even really matter what a topological space is. But what matters is that these things appear very commonly, all right? And you can take these objects and you can look at what's true inside the objects. Basically, you can define a logic associated with these objects about what they think is true in some sense, right? So internally to these objects, there's a notion of quantification, and there's a notion of set, and there's a notion of subset, and there's a notion of implication, etc. And you can say, okay, well, these notions, they mean something from the outside, and we're often interested in the outside view of these logical notions. But you can just look at it from the inside and say, okay, well, inside, if I interpret these as sets, what does this logic look like? And it turns out that what all of these toposes share in common is that they are a form of intuitionistic set theory. So if you take classical mathematics, right, and you look at these objects like sheaves over a topological space, and you look at the logic inside that structure, it satisfies intuitionistic logic, right? In general, it very much does not satisfy classical logic. And that's kind of fascinating. And I also think it's kind of exciting because now all of a sudden, here's a reason for mathematicians to care about intuitionistic logic. It is something that is true inside every topos, right? So if there's a topos you care about, and there's a theorem of intuitionistic logic, then for free, you get a property of that topos, right? In particular, if you can prove, intuitionist logic is going to be a subset of classical logic, but you can prove all these interesting theorems that, just don't use excluded middle. You can prove very basic things like, stuff about sets and bijections and cardinalities and a whole bunch of things. And if you can prove them without using excluded middle, then automatically they hold in these toposes. And maybe even your topos satisfies additional properties, which are non-classical properties. Maybe it satisfies all functions over the real numbers are continuous, right? Maybe it satisfies that property. And logicians have studied these properties. And so you can just open a logic book, take a theorem from that, and apply it to your mathematical universe. So I think that's really exciting. And I also think that that's kind of this, like, I don't know, this fascinating application of logic to mathematics where, most of what logicians do, mathematicians don't care about that much. But here's a realm in which, like, ordinary mathematical objects that are, advanced mathematicians care about turn out to have this connection to logic, which is really profound and actually, salient, right? It's really useful because some complicated questions about complicated toposes become reasonably simple questions in intuitionistic set theory.
That is really cool. That is really cool because, as you said, yeah, there is a lot of well-studied properties on intuitionistic logic, and then it also comes down to computer science as well, because that's how what we care about the logic too, right?
Yeah.
Yeah. And
I
go on.
Yeah, go ahead. I was gonna say it'd be a whole other episode just to talk about sheaves and what they mean and why you
Yeah,
might want
yeah,
to care about them as
yeah,
a computer scientist. But again, I'm not sure I'm the right person for that. There are so many
yeah.
people who have done all this work.
I think it would be very hard for myself to follow those, because category theory is definitely where you start to really lose me.
Yeah. I agree. I sometimes I feel like you can really avoid talking about categories in some ways.
Really?
Well, I mean, I haven't talked about Kripke models, but Kripke models are a thing, and they turned out to be a very simple, very very simple example of a pre-sheaf category. And yeah, you don't need category theory to talk about them. You can just say, okay, Kripke models are a model of intuitionistic logic, and I haven't explained what a model is, but basically they're a world in
Before
which you can understand
before
intuitionistic
we
logic.
get into it, why do you think category theory is so popular right now, like in computer science? Because it feels like it's so hot. Everyone is kind of in a way talking about it and want to do something on it. What's going on?
Yeah, I mean, I'm not sure, right? I definitely, every 6 months, I'm like, oh, I love category theory. I think it's great. And then 6 months later, I'm like, why? Why
What
is
am
it
I
so
doing with my
popular?
life?
Yeah. So I think at its very most basic, this notion of world in which you can interpret things, that's what people want, right? This is a very appealing thing about mathematics when you can say in an abstract language something that's true about two completely different kind of fields. And I
Hmm.
referred to group theory at the very beginning.
Right.
Group theory was already one of those things, right? At the
Right.
time where these techniques were developed, people were talking about permutation groups, right? Groups of shuffling. People were talking about symmetry groups, right? You take a shape and you look at it, you look at transformations that preserve that shape. And people were also talking about, the natural numbers or the integers mod, mod 8, or the integers mod some prime, right? And all these things were completely disconnected. And then group theory came along and it unified all these concepts. And now you can just say, okay, well, here's a theorem that holds for all groups or for all abelian groups. And all of a sudden you have this powerful, deep current that carries with it all these theorems and all these crazy different fields. And it's just this like magic wand. And it's just the absolute, I think it's really cuts to what makes math exciting is that you sometimes you get this insight, and it's this very deep, very profound insight that connects all these different things together. And I don't think there's any other field where you really build these like deep connections like that. And category theory really seems to be this like amazing like group theory on super steroids, right? It's like
Yeah.
the definition of a category is actually not that dissimilar to a group.
Right.
But
Yeah.
then in category theory, you can start to formulate these completely categorical notions, and you get at a much more advanced level than group theory, you get these kind of deep connections between these very different fields. And I think originally categories were developed to make connections within the field of algebraic topology. And that
Mm-hmm.
was already a powerful thing, right? You could already have this very simple, well, relatively simple concept that unified these very different, very complicated things called cohomologies. Again, I'm like at the very edge of my knowledge, but what happened a few years later, not that long, was somebody, I'd say essentially Grothendieck, but Grothendieck and others found a connection between this and algebraic geometry, and that even carried over to number theory. So this incredible thing, this incredible connection was created between algebraic topology, where we had all these powerful theorems, and number theory, where it's like it's really hard to prove anything. And it allowed people to solve these really hard problems. And this is very exciting. Like, to a mathematician, when I was young, I was like, this is incredible, right? This is like the most powerful thing you could know. And so I think there's some of that. And I do also think that, yeah, when I started basically computer science, right, there was already category theory in computer science, but it was kind of a niche subject. And it was very, it didn't feel like it had really this deep connection that all these other parts of mathematics had. But in the last 15 years or so, now it's like really connecting up, right?
Right.
Type theory and category theory and all these other parts of mathematics are just getting like sucked up. And I think it's very exciting to see that connection. Um, I also think there's a certain amount of like, it's a, when other people say this is cool, then you think, well, there must be something to it. And, eventually you learn category theory and you learn how to talk in category theory, and then nobody else understands you. So like, oh, maybe I should learn category theory, right? So, there's a certain amount of like, this is how people talk nowadays. They use all this
Right.
complicated
True.
language, but there's
True.
also something deep there, I think, and appealing. And certainly it's hard to talk like the generality of what this language of topluses is and these sheaves.
Mm-hmm. Mm-hmm.
It's very, yeah, it's very categorical in the way it was originally formulated. And if you want the full generality, yeah, I think it's hard to do away with category theory because, now that's how it's formulated. So, so there's the appeal for you. I don't know if that's enough. I do
It
think
is. It
that,
is.
yeah, there's a very, I think people think that about mathematicians in general, right? They have this crazy language and these crazy notations. But yeah, category theory feels a little bit extra. And I don't know. People already complained about this in Grothendieck's era. So like in the 50s, people were already like, what? Why do you have to do all this like crazy abstract stuff?
Well, no, I think you definitely answered my question in the sense of I was a little skeptical in a sense for if it's actually all of that, or if it's that actually useful, and if it's necessary to be talking about those ideas in computer science, but the way you answer, there is definitely, mathematics is also a sense of beauty and personal pleasure too, right? Like
Yeah.
we're proving these things because that's what we think it's nice to be working on, and that gives us some personal satisfaction. I was trying to explain the
Definitely.
other. I was talking to this person that works in she's a postdoc in some subfield of biology, and she was talking on how they get their problem and they will have to solve this particular problem for doing this particular sort of stuff. And she was asking, how do we pick our problems in computers, in my field, in our field, type theory and programming languages. And I'm like, well, most of the time we just work on whatever we feel like, and then later on we figure out how to sell it to other people.
Yeah, I think this is a common question in mathematics for sure.
Yeah.
I you know I think it's like any field of mathematics. There's things that come that are like applied and useful, and I
Right,
think type
right.
theory
Yeah.
has that, right? You want to prove things about programs because some of them are running on a plane, and so you need a logic, and you need to talk about computation, and you need to talk about semantics of computation, and you need yeah.
One thing
Um,
leads to another as well. There's a build-up going on there
right,
too. But now, why do you want to talk about the semantics of this particular program? That's another, like, you didn't have
right.
to. It's just some
Yeah.
personal interest going on, and then later show, oh, this is actually interesting because of this and that,
Yeah,
right?
yeah.
So
And
yeah,
sometimes it comes full circle, right? Like auto
right,
math, you know,
right,
and then Martin Luther type theory is like answering some philosophical questions, and then
right,
Cock
yeah,
answering more philosophical questions, and then oh yeah, but actually you can use Cock to prove stuff about planes, and
yeah.
software that runs on planes. And so it's a long walk, but yeah, I also think people that fund science know that they know that yeah, it's not always obvious what's going to pay off, and they also know that the beauty there's something there, right? It's hard to explain the beauty of mathematics, but there is something there. And it's much nicer to show pictures of black holes or whatever this what is it called, this new telescope. But once in a while, people do get excited about these math problems, especially the ones you can explain, right? The simple math problems. And I think there's this beautiful the category theory, whatever. I'm digressing, but people talk about theory builders, right? People that really try to understand the connections, the bridges, and the deep reasons, and the problem solvers, people that are trying to like prove Fermat's last theorem or the P
Right.
versus NP
Yep.
conjecture.
Yeah.
And
We
those
need both of
two,
them.
yeah, we really need both of them, and also both of them are kind of beautiful in their own way, right?
Yeah.
There's
Yeah.
there's the Sudoku solving, and there's and there's the painting of beautiful, yeah, finding this beautiful you know story of the universe.
Right. It's funny you mentioned Sudoku because I had a professor one time. Like, I think first time I was learning programming languages, we were doing some trying to come up with some things, functional programming, and he was
Mm-hmm.
like, "You guys can pick whatever projects you want. Just don't pick a Sudoku solver. I hate Sudoku."
That's funny.
Right. And apparently some people just, according to him, there's no insight in Sudoku. It's all mechanical, right? i
Hmm.
can I can see that in a way,
I
but
I'm not sure that's actually true, but
it's not.
again, this is
It's
a
not.
subject for
Yeah.
another day. I do. I mean, Sudoku is NP complete, right? So I think at
Mm,
some point,
mm,
you're like, okay, well, the insights of Sudoku are
right.
actually the insights of constraint, just general constraint satisfaction, right?
Right.
You
Right.
solve SAT, and and solving SAT is interesting, I think. And I don't know, Sudoku is just yeah, it's a
Another
toy.
problem. Another
Yeah.
toy problem. Yeah, for
Hmm.
sure. So another thing that we were, after all this digression, but it was a nice conversation. Another thing that we left behind that we had to pick up was about Kripke semantics and some notion of models and model theory. As I mentioned at the beginning, I think I definitely mentioned at the beginning of the episode that this notion of building a model for something keeps creeping up, and it's not quite clear to me what a model
Right.
is.
So I'm not sure I can define it in the most general terms, and that's kind of annoying. I mean, when you Google, model theory and Gödel's completeness theorem, they're actually talking about a particular notion of model for classical logic, and that's a particular notion. And so the most general notion, again, is more philosophical. But generally, what you have is you have your logical theory, and that's just a syntax that basically says, here's a string of characters or something more structured, like, a logical proposition, and here are rules to deduce different propositions. And this is a very syntactic object, and you can just study it syntactically like you study numbers or like you study trees or anything in computer science. And people actually usually call that structural proof theory or just proof theory. But of course, all these symbols actually mean something, right? If you have a logic where you just have, variables and, a binary function that you call a binary predicate that you call less than, all right? You can talk about the syntax of, for all x less than y, or for all x, there exists y such that x is less than y. All right. This is just a string of characters without any meaning. And then you can talk about axioms and whether you can prove that string of characters and yada, yada. But also, of course, you can assign meaning to these things, right? Where you say, okay, well, actually, the for all quantifier is talking about every possible x in some domain. And the less than operator is actually less than, in the real numbers, say. And then you can say, okay, well, for all x, there exists y such that x less than y actually means something in the real numbers. And the thing that it means is that every real number has another number that's bigger than it. And that happens to be a true thing in the real numbers that we know about, right? We know about the real numbers, and we know what it means to be less than or equal, for a real number. And that's basically what a model is, right? A model is a way to interpret all these logical symbols in such a way that you can interpret these sentences. And the model of a theory is usually an interpretation that preserves truth, right? So if I can prove it, it must be true, right? Usually that's a theorem you have to prove, and it's called the soundness theorem, right? So a sound interpretation is a way to associate meanings to characters in a way that preserves truth. And completeness is the other way. You say, if this is true in every possible model, then actually I could have proven it syntactically using my rules of my logic. And this way of associating models to theories and talking about the truth in those models is the way most people do logic. And it's, proof theory is actually kind of in the minority. Most people look at models to understand whether something is true or not, or consistent or not. So what about consistency? Well, typically you're going to build a notion of model in which there is no model of false, right? Or there is no model of 0 equals 1. And that means that, if you can actually prove that there's no model of false, that means that there's no proof of false if you have soundness, right? Because any proof of any proposition is going to be true in every model. And if there is no model that satisfies false, then there can't be a proof of false, because otherwise it would be true in the model.
Is this what it's called, the Gödel completeness theorem?
No. This is much simpler. This is
really?
just soundness of first order arithmetic, right? So
I see.
Consistency of first order logic is very simple if you have the notion of model. Now, of course, the notion of model itself requires you to have a lot of things in your meta theory, like sets and interpretations and things that might be less plausible than just syntax. But at the very least, if you can do that, you can look at models and you can prove consistency. And yeah, it's very simple and straightforward. And then you can start talking about models, and it's usually much simpler to talk about models than to do all this syntax, proof
Right.
theory stuff.
Yeah, yeah. In a sense, it feels to me that models and realizability are kind of two sides of the same coin, right? Like, because
Yes, absolutely. So realizability can be seen in a certain sense as a model of intuitionistic logic.
right.
And in particular, remember I talked about these universes called toposes?
Mm-hmm.
Well, these are actually models of intuitionistic logic, right? There's an interpretation for each construct in intuitionistic logic into any topos. And there is a particular topos called the realizability topos, where the all the inhabitants of the interpretation of a proposition are the realizers. So it's kind of nice, right? You can really apply this classical notion of model theory and end up getting realizability, for free, basically. I mean, you have to construct the model. It's actually non-trivial. But originally, I think people didn't, it wasn't obvious how to use model theory the same way you use realizability theory, right?
Right.
It seemed similar in some ways, but people didn't really understand the connection. And I think people pieced it together late 60s, early 70s. They realized that actually, yes, model theory can explain realizability in some sense.
That's very interesting. Just a off topic. Can you hear some noise on your side?
Yeah, it sounds like rain
It's raining. Yeah,
on your windowsill. It's
it's
actually a
definitely.
nice sound. It sounds very nice.
It's very soothing, huh?
Yeah.
Um, well, I'm thinking of. I don't want to pollute my soundtrack too much. I'm thinking of start heading towards the end. If that's okay.
Yeah. We've talked about a whole bunch of stuff.
Yeah, yeah, and it's also a very dense episode as well, in the sense of we talked about a lot of different proofs and
Yeah. A lot
methods.
of
So
different
yeah.
things. I mean, like I said, this is, I would say, maybe an intro graduate logic course worth of content, to be
Yeah,
honest.
just touching very different
Yeah.
subjects, just to give a sense of what are the amazing things that we can actually go out in the wild and study ourselves, and
Yeah. It's
each one of these
definitely,
each one of these topics are worth PhD theses on their own.
yeah.
Probably a couple of decades ago, but still.
Well, I mean, people do still think about these
Right,
subjects,
of
right?
course, yeah.
People have learned a lot over the
Right.
years, but all these subjects are still active. Yeah,
So
and go
we were
ahead.
talking about models and realizability proofs, and I think that the last point that was left behind in this particular realm was the notion of Kripke semantics.
Kripke semantics,
Is
right?
that
So
mhm.
yeah, so that ties into everything, right? So at the time, I think it wasn't obvious. Yeah, so you could build a realizability model and then show that the disjunction property holds, um, but but there are a lot of questions about intuitionistic logic where it's like, okay, what can't you prove in intuitionistic logic? What can you prove? And what model theory is very useful for is showing you can't prove things, right? I mentioned how you can use it to show you can't prove false, but really the only way, the only easy way to show you can't prove something is to build a model where that thing doesn't hold, right? And then have a soundness proof. So
Wait,
so if you
wait. Can
have,
can you stop there 1 second?
yeah,
Let's see. Let's see if I follow. So the only way to show that something does not hold is by building the model and showing that it doesn't hold there. Wait.
right. So the question is, So showing you can prove something is pretty easy. You just build a proof, right?
Right.
But showing you can't prove something, you'd have to show that every possible proof is going to fail.
Gotcha. So then by building
But
the model and showing that it doesn't hold in the model now sits in a more powerful logic system,
yeah, like
probably.
to show something is provable, you only need to build one proof, right? You just need to build proof. But to show something is not provable, you sort of have to look at every proof and say, okay, this proof doesn't work. But if you have soundness, you say everything that I can prove holds in every model, then you just need to build one model where it doesn't hold, say, oh, there can't possibly be any proof, right? So in some sense, models are to non-provability what proofs are to provability, right? You
Ah,
give one proof, you know that it's provable. You give one counter model, one model where the thing doesn't hold, you know that it can't be provable.
that's beautiful. I love it.
Yeah. And I mean, of course, like in computer systems, when you try to prove things, you're basically doing both at the same time. You're looking
Right.
for proofs, and you're also looking for counter models.
Yeah. Like as you're doing the proof, you're building the intuition of why certain thing does not
Yeah.
hold up as well.
Yeah, exactly. And so Kripke models are a model, basically a notion of model for intuitionistic logic. And I mean, the way they work is you take classical models, right? So models where everything is either true or false. And then you give a notion of time where you sort of say, okay, this is true at this time. This is not true at this time. But in some sense, you learn new things as time goes on, right? So at each given time, you have a model where some things are true or false, but some things are left undetermined. And then you can like easily show that this notion of model like allows you to exclude the excluded middle, for example. You can show that there's a model in which A or not A doesn't hold, and that's basically a model where there are two possible futures: one where A eventually holds, and one where not A eventually holds. And then you ask, well, okay, so what's true across all time? Well, certainly not A or not A, right? Because there are two possible worlds, right? Where in one of those worlds A holds, in one of those worlds not A holds. So Kripke semantics is sometimes called possible world semantics, and it is a way to give a very classical mathematical framework where you have models for intuitionistic logic. And what's kind of nice about Kripke models is they're complete for intuitionistic logic, right? So anything that's provable in intuitionistic logic is exactly the things that are true in all Kripke models. And here's another thing that kind of dovetails nicely with everything we said before. It turns out that topos semantics is actually a vast generalization of Kripke semantics, right? So this possible world interpretation, where you look at, things that are true over time, is actually a special case of this general category theory world, where instead of having time that goes by, you have a general category of worlds. And I think that's all I really have to say about that.
This stuff
Again,
that you're
there's
talking
a whole
about,
course on this.
this stuff that you're talking about, Kripke semantics or any Kripke models, brings to my mind the notion of model logic.
Yeah,
Are they
of
related?
course. Oh, I mean, you can build, yes, you can build Kripke semantics for modal logic as well. And that's kind of not a coincidence, because you can actually so that's the model theory view is Kripke semantics works for intuitionistic logic. It also works for modal logic. But the syntactic view is that, you can just take intuitionistic logic and embed it into a particular modal logic called S4. And it
Right.
turns out that embedding is is faithful, right? The things that are provable in intuitionistic logic are exactly the things that are box provable in S4.
There you go. Gotcha.
And so so modal logic, is an appropriate language for both. And there's a proof theory view, which is this embedding of like turning true intuitionistically into box true classically. And and then of course the category theorists have like thoughts about this, but I don't understand them.
I don't understand modal logic to begin with. That on its own is another episode just on its own.
Yeah. It's definitely not my one for me. It's a subject I really know nothing about. But it, like I said, Gödel did everything about everything, and he
true.
he proved a lot of these theorems about modal logic and intuitionistic logic. He proved the double negation translation. He proved the incompleteness theorem. He proved the completeness theorem. So he was like, he was everywhere. He proved he proved that you couldn't refute the continuum hypothesis, right? He was everywhere. He was just this like absolute titan.
Right. Yeah. Gödel was definitely something. Well, I think
some days I'm like, I'll make a podcast and it's just going to be the Gödel podcast where I just talk about Gödel.
You should. You should. I love that idea. Go for it. I
certainly can't invite him, but maybe.
That is awesome. I definitely get behind that idea. I love it. That would be great.
Thanks.
Yeah. Well, I think we covered much of what we wanted.
That was impressive, actually.
I have one quick question. You just give me a quick definition. Let's not go too deep into it. But I thought it was very, very cool, the notion of what's the Markov principle.
Yeah. Actually, so the Markov principle is just a very special case of the excluded middle. It just says that if it's not true, so if you take predicate, so some proposition with some talking about some natural number, right? N. So say n is greater than 3 or n is a prime number, some predicate. Okay, and if that predicate is decidable, right? So those two examples I gave are actually decidable. N is prime number, there's an easy decision procedure for that. N is greater than 3, great. All right, so what the excluded middle gives you for free is if it's not the case that there exists if it's not the case that there exists an n such that a of n, all right, then actually there exists an n such that a of n. All right. So if it's not true that there is, an n that satisfies that decidable property, then it just exists, right? By classical logic. All right. Another way to say the same thing is if it's not true that every n does not satisfy the property, right? So you push one of the negations inside. If it's not true that every n does not satisfy it, then there exists some n that satisfies it.
So it's in a sense as if you're undoing the CPS transformation that we were talking about. You do the
I guess. You're just saying, if not exists, then exists. Yes, it's definitely the other direction of that double negation. And that's true classically in general. For any a of n, if you put not exists, then you can prove exists. But intuitionistically, of course, this is like exactly what you don't want, right? You don't want this principle in general. But if a is decidable, then you can assume this principle. You can say if not, there exists something such that a of n holds, and a is decidable, then there exists n such that a of n holds. And you can show that this is consistent with intuitionistic logic and doesn't imply the excluded middle just by finding an interpretation in realizability. So how do you find that interpretation in realizability? Well, you build a realizer for that proposition. And it's basically a realizer that takes in this basically content-free proof that something doesn't not exist and finds an instance of that thing. Well, what's the realizer? And the realizer here is just a program that checks every possible natural number and stops when it finds one that satisfies it. And then sort of meta-theoretically, you can sort of reason by classical logic and say, oh, actually, that program is eventually going to stop because you know that it's not going to not stop, right? And so, right. And so this is something you can assume. And it also is weaker than the full excluded middle, but it's super useful because it'll always give you some, it allows you to like assume this program that finds things, and that's useful in a bunch of contexts. What's kind of tantalizing is that you can't assume that in a bunch of other really reasonable things that you can assume in intuitionistic logic, like every function is continuous. I think that every function from reals to reals is continuous is something that's consistent in intuitionist logic. But if you add Markov's principle, then you're out of luck. You're inconsistent again. And understanding why that's the case is kind of interesting for the same reasons I said earlier. It's kind of, from the outside, both are true, but then you can't have too much knowledge about yourself from the inside or you get inconsistent.
All right. I think that ends our episode in a very high note. That was great.
Yeah, I had, again, so much fun. I love talking about this stuff. You're a great host. Like, I can't say that enough. It's really great to talk about you and like have your like energy and curiosity.
Thank you so much, dude. This was really good to have you over. Hopefully we can work together in the future and you can come and co-host some episodes. We already have some plans for the future.
Love that.
And well, that's it then. See you guys next time.
Right.
Well, that was it for today's episode. It was a different episode, right? It was very dense and packed, full of concepts, full of proof sketches. What do you guys think? Did you guys like it? Could you learn a thing or two? Could you follow the proofs? I'd like to hear what you guys have to say. If this is a format of episodes that you guys would like to see more, let us know on typetheoryforall.com in the comments section, or you can even send us an email at typetheoryforall@gmail.com, or you can tag us on Twitter at ttforall. Well, that's it. If you guys liked it, I'll try to make more episodes like this. Maybe bring other guests that do this sort of stuff as well. Now, that's kind of what I have for you guys. As a personal note, I am taking a sabbatical year, so I'm going to Brazil next week, and I'm not sure how things are gonna go with the show. I will do my best to keep it monthly, to have at least one episode a month. I'm already talking with some possible guests here and there, but I really don't know how things are gonna go. I need to relax and be with my family. I'll also take this opportunity to remind you guys to take care of yourself, take care of your mental health, take your own time, go through life in your own pace, because only you live your life, man. I see you guys next time.